We begin our workshop with the first technical talk on evolving trends of digital signatures by Dr. Balaji Rajendran C.
I'll just be setting the context for today's program. So that's the idea. So I start with the question. So what is think is required for secure communication between two parties, a sender and a receiver? Secrecy or confidentiality of their communication, right? Because when two people speak, they want to keep it themselves and they don't want to share it with them. So that is sharing with others. So that is the objective. Second is authenticity of their communication. That is, let us say that if A is communicating with B, A should be sure that he is really communicating with B, and B should be sure that he is really communicating with A. Third one is integrity of communications. Suppose when communication happens, nobody is able to tamper the communication, that is integrity. The last one is non-repeatability of communications. So that is a tricky part, where one is not able to deny that he has communicated or this has sent the message. So these four are very important points. So just let us see that how we can look into this. Now let us say that suppose you receive a signed document, you have to do an integrity check. That is, if someone has altered the content of it after it has been signed, that is the integrity part. That is basically a content alteration or corruption of it. Then second, you also do an identity check, whether the person who has claimed to have signed, has it really signed or not. So that is the point. So basically you perform an impersonation check, that is whether if somebody has signed and you think that signature is not matching with someone else, the claimed signer, then basically it is an impersonation attack. So this process is actually called authentication, that is where we are verifying someone against their claim. So that is the thing. And identity is established through authentication. So I'm just showing you some simple scenario where two people, we can take them as Jay and Viru or Alice and Bob, whatever you feel like. So now basically when two people are communicating, an attacker can come in the middle and he can try to get it. So this is basically an attack on confidentiality or secrecy. Then there is an attack on authenticity or spoofing, where say for example here, let us say that in this context where Jay and Viru are there, there is a third party, Gabbar, who is coming and saying that I am Viru, send me all the corporate communications with ABC. So this has actually been happening there. So that is the thing. So attack on integrity, basically you can see that, say for example, when there is a transfer happening, an attacker can come in the middle and try to alter the communication. So this is one of the things. So attack on non-repudiation is something like this. Say for example, probably Viru is sending to Jay, saying that initially he or she says that please send me on confidential document. Then later says that after receiving all of the things, he or she says that I have never asked for any confidential documents. So this is basically going back on non-repudiation or going back on whatever that is said. So this is basically a non-repudiation thing. There is a breach of this is a mistaken thing. Please ignore that. So that is the point here I want to say. Non-repudiation is a tricky part where you go back on whatever you committed. So that is the thing actually. Non-repudiation is the ability of not allowing you to go back, not allowing you to go back on whatever you have committed. So that is the thing. Here basically it is a attack on non-repudiation. So that is what this slide is actually showing to you. So the basic elements of trust are these four properties, that is confidentiality, authenticity, integrity and non-repudiation. If any system which can assure you all of these four properties, we can trust the system digitally. So today, as of now, the only system which can offer you is the public key infrastructure, which can cover you all of these four properties. And of course, it is fully backed up by the laws and policies. As far as India is concerned, we have the Control of Certifying Authorities, which is being backed with the Indian IT Act, and meaning of course regulated by policies, and they adopt the global standards, And of course, it is up to the implementers, like developers like us, to ensure that everything is in as per the defined code, including the technology. So before I proceed further, I just want you to reflect on hand signature. Can you teach me how to sign like you? So obviously, it is difficult for anyone, for others to mimic or imitate, and even it is difficult for yourself to teach others to reproduce exactly the same way that you have been doing. Difficult to change, right? Because suppose you want to change your signature, you try to do a number of hours of practice to change your signature after time. And then there is a unique pattern. Though you are writing the same words, whatever it may be, it is extremely difficult for someone to mimic that pattern. It is very difficult for you to reproduce, teach the pattern to others. So this is very kind of what I can say is a secret which has got ingrained within yourself. You know the secret, but you cannot share that particular secret. So that is the unique thing of an hand signature. So now let us come to the concept of digital signatures. So for digital signature, it is basically a value, ultimately a mathematical value, which is derived from two values, A and B, we can say. One is basically a secret which is known only to you, okay, the signer. And then another one is basically a digital fingerprint of the message which is being signed. So now digital signature can assure you authenticity, integrity and non-repudiation. Okay, and a digital signature will look something like that, whatever I showed on the right hand side. So what is missing? Digital signature. What is the trust element which is missing here? I said 4 elements. Privacy or confidentiality. Okay, so that is actually not covered by digital signature. Digital signature provides you authenticity, integrity and non-repudiation. Of course, the concepts of PKI also provide you confidentiality. That will cover in the later part of the session today. So now let me start with a problem, or a very imaginary problem, where a couple of people are sitting together and they are saying that each of you get a secret number that is unique and will be identified by that number. So do you think that this is possible? I should come with a number, but I should not share it. At the same time, it should be unique, and I should also be identified with that number, right? So this is the basic premises. Of course, it is not possible with a single number. So what we do is, we come up with a pair of numbers, okay? So let's generate a pair of numbers. One of the number in the pair will be kept secret, that will be called as a private key. The other one, which can be shared, is called as public key. So the public key cryptography, whatever I am talking about, PKI, so that, public key infrastructure is dependent on public key cryptography, and public key cryptography is basically because of this. Because there are a pair of numbers, one of the number is kept secret with you, other one is actually going to be shared with anyone and everyone. So that is actually the solution. So with that, the public key can be used for identifying ourselves, and private key can be doing for the operations that we are going to do about it. So with that, I'd just like to get more into it. So digital signature, for creating a digital signature, every individual is going to require a pair of keys. One of them is called as a public key, which he can share it and distribute to everyone. Other one is called as a private key, which is going to be known only to the owner of the key. And these public key and private key are mathematically related with each other. And in such a beautiful way that if you do an operation with one of the keys, let us say public key, you can reverse it using the private key. If you are doing an operation with the private key, then you can reverse it using the public key. So this is the kind of thing. An analogy can be something like a very imaginary lock, where you have a pair of keys, but you have to use only one of the key for locking. If you are using one of the key for locking, the other key you have to use it for unlocking. So something like that. Okay. So if you are using private key for locking, then you have to use a public key for unlocking. So this is the kind of thing. So for digital signing, we always use a private key. If I have to digitally sign a document, then I need to use my private key for digital signing. So this will be for doing that. And for verifying, suppose I send the digitally signed document to you, for verifying me, you have to use my public key. Because whether really I have signed or not, so you will use my public key. private key will never be shared with anyone and anybody. Okay, private key will be kept as a secret with myself only. So this is how it looks like. So this technology is called asymmetric key cryptography, as Director Sir was mentioning. So the good thing, or what is the main thing about public key cryptography, is that I am sharing my public key with everyone, but I am keeping my private key as secret. But you know that they are mathematically related with each other. So you may be wondering that what if someone, a mathematical genius, can break or find out the public key from the private key. So, but by looking at the, looking at the encryption key, you cannot get the knowledge of the decryption key. So that is the point. So say for example, if I look at the public key, I cannot find out what is a private key. So basically, I am trying to say a word called computationally infeasible. So what I am saying is, I am not saying impossible. I am just saying that it is computationally impossible to do the reverse calculation and find out what a private key is given a public key. So this is what I am trying to say here. So computationally infeasible in the sense, it actually requires a huge, enormous computing power, and which not only require computing power, and you need to run a traditional computer for several years altogether, continuously maybe probably for 50 plus years to get your, derive your private key from a given public key. So that is the kind of thing which is required. So let's say key pair. So this is how the key pair is, private key and public key. This is how the pair looks like. So again, to reinforce whatever I said, that let us say that there is a document, you encrypt with your public key, then you need to decrypt with the private key for getting the original text back. Similarly, there is a original text, you encrypt it with the private key, that means you have to decrypt with the public key for getting the original text back. So this is how it looks. But if you try to do the other way, that is, you encrypt with the public key and try to decrypt with the same public key, it is not going to work. You encrypt with the private key and try to decrypt with the same private key, it is not going to work. Okay. So now let me get into the part of digital signing. So the second step, actually I said that digital signing consists of two values. One is a secret, which is known only to you. Another is the fingerprint of the message. Now, to generate the fingerprint of the message, what we will do is, we will use the cryptographic hashing algorithm for creating the fingerprint of the message. So this is the message, I pass it to the cryptographic hashing algorithm and I get the fingerprint of it. So the beauty of this algorithm is that any small change to the input will produce a totally drastically different output. Say for example, in this thing, there is a dot in the second part, 3 p.m. full stop. So that dot actually has created a totally different output, right? Because of one small change. Now you may be wondering, what if there was no dot but there is one blank space? Then also it will give you a totally different output. Okay, the output will be going to be totally different. The digest are going to be different. And this is a one-way process. Actually, please do not confuse hashing with encryption, because encryption is something different. Hashing is basically a one-way process. That is, you give an input, you get an output. Okay, again, let us say that I get the, pass on the output back to the hashing algorithm. I won't get the original thing back. Okay, this is not possible. I won't be able to get the message as I J in the part. That is not possible. So instead of that, what I will get is another hash value or another fingerprint of it. So this is what I will get. So these are certain properties of the cryptographic hash function which creates a digital fingerprint or representation of the message. It produces a fixed size output. Whatever the size of your input may be, a number of characters, the output is going to be a fixed. 512 bytes means 512 bytes only. And any small change to the input is going to produce a totally different output. Number of algorithms, of course, MD5 is now not used because it has been already broken. There are algorithms like SHA 1, 2, and 3. So carrying forward, this is the digital signing process. So you take the fingerprint of your message. Please remember, I am not taking the message. I am only taking the fingerprint of the message and then encrypting with my private key and then getting my digital signature. So this is what I am doing. Okay. So so the digital signature is finally added to the document and sent to the receiver. So this is the process. So now let me just graphically illustrate this. A sender is composing a message, sending it to a digest, crypto hashing algorithm, where it produces a message digest, and this message digest is encrypted with the private key of the signer, and then it is added to the digital signature. It creates a digital signature. When you are encrypting with the private key, it produces a digital signature, and that actually it is sent to the combined with the message and sent to the receiver. So now the verification, now the signing part is over, now I have to verify. So what I can do for verification, I receive a message like this. So what I do is, first thing what I do is I take out the message part and put it to the same hashing algorithm whichever the sender used. Sender has used, let us say, SHA SHA algorithm 3, then I use the SHA 3 for generating a digest. And this is the digest that is computed for the verifier, that is myself, in the top one. And the bottom side, the signature part I take out, because since you have claimed that you have signed the document, then I will use your public key, because you had used your private key for signing the document. So I will use your public key for verification. So I will use your public key and decrypt it, which means I will get the digest that you calculated at the time of signing. So that is the one which I will get. So now I will compare these digests with both the things. If there is a matching, then there is no issue. That is, the message has been really signed by you and message has not been changed since you signed. That is, authenticity and integrity are preserved. If there is anything, then I will discard the message. So the same thing explained in a graphical format. I receive a signed message, and what I do is I take out the message part, put it to a message fingerprint algorithm, which will give me the message digest of the message. And then there is a digital signature which I will decrypt using the signer's public key, which generates the digest which generates the digest that you calculated. If both are equal, then the message has really come from you and nobody has altered it. If there is a small change in the digest, that means there is somebody has tampered the content. So then in that scenario, we have to ignore the message. So I just want to re-emphasize a very important point here. Unlike our hand signatures, generally we do not change the signature when we sign different documents or papers. Our signature remains the same. But in digital signatures, a digital signature is dependent on the signer as well as the content. So today I am signing some, yes sir.
You mentioned the basic part 5. I was just wondering, when we usually take a look at the entire structure of the entire thing, there is usually for all online processes, we also check whether the certificate has been revoked.
Yes,
because there is
absolutely.
certificate revocation,
Yeah.
etc.
Yeah.
So is that not part of this verification?
Yes sir, it is coming sir. I am just coming to that point. Right now we are only dealing with the problem of integrity and authenticity part. I am just coming to that part. Just coming in a few slides. I'll cover. So digital, yeah. So digital signatures are basically signer and content dependent. Suppose let us say that you can look at the third and the fourth example. The meaning is same, but there is one small character change. E is capital and the last one, the fourth one actually E is small letter. The signature is totally different. Suppose if you sign this document, then the signature will be different because your private keys will be different. It will not match with me. Okay? So that is the thing. Your keys are different, my keys are different. So that is the thing. So a small quick recap, whatever we discussed. Digital signature is a value which is derived based on the digital fingerprint of the message, that is the message digest, and the signer's secret. This establishes identity and authenticity of the signer, integrity of the document, and but non-repudiation can only guarantee certain extent. Why certain extent? Because now let us say that I have digitally signed a document and sent to you, and later I say that I have not sent it, or my keys have changed. I changed my mind, I changed my keys, or my key has been taken over by somebody. In that case, the non-repudiation cannot be guaranteed. So that is where we need the concept of digital signature certificates, DSCs. So certificates are required for firmly establishing the ownership of the public key. Who is owning the public key? So we need not actually have to certify the private key because public key and private key are entangled and twinned together. So if I say that who owns the public key and if I have certificate for that, then it is perfectly fine. So DSCs are sufficient for providing a strong mechanism for non-repudiation, that is the inability to deny. So DSCs are the documents which provide the ownership of the public key. So DSCs can contain the name of the person, public key of the person, validity of that particular certificate, and it should also have the signer who is issuing the certificate. That is very important. Now, there is a small catch here. So for example, let's say that if I sign as a person, public key, then it will not be actually be sufficient. Meaning you won't be agreeing. So we need, all of us need a trusted third party. So that is where we come to the concept of certifying authorities, who we call them CA. It's not chartered accountants, but certifying authorities, CA. So CAs are the entities which issue the digital signature certificate. They are the trusted third party, and they form the public key components of the public key infrastructure. Their responsibility is to verify the credentials of the person requesting for the certificate. Suppose now say that I request for a digital signature certificate, my credential has to be verified. They may ask me for my Aadhaar card, whatever valid identity card, and then they give me the certificate. They issue the certificate, they revoke the certificate. Suppose now I say that my keys have been misused, then I have to report to them, my certificate will be revoked. Further, there won't be any trusting of that. So I generate and upload the CRL, certificate revocation list, where suppose if there is this thing, certificate has been revoked, that serial number of the certificate will be placed in the list. So for regulating all these certifying authorities, we have CCA, Controller of Certifying Authorities. So their vision is to create trust in electronic transactions, as Sir has mentioned, and of course they oversee the functioning of the certifying authorities. They certify, because basically they give a certificate to all the certifying authorities, and certifying authorities give certificates to us. Suppose I am a subscriber or an end user, I ask for a certificate and I am being given by certifying authority. Certifying authorities are actually regulated by Controller of Certifying Authorities, who, meaning they issue a certificate to them. So that is how the process works. So the details are there in cca.gov.in website also. So these are some of the functions which Sir has already mentioned, the other functions which has been taken out, but this is a very brief of it I am covering here. So as we go on, this is how the certificate will look like. You can see on the left hand side, the certificate issued to me by one of the certifying authorities, and next is my public key, and third you can see how the trust is flowing. The trust is flowing from CCA India. From CCA India we go to SafeScript CA, who is actually an authorized certifying authority operating under CCA, and they have given a certificate to mine. So that is how it is actually. So this is the model in India, National Route Certifying Authority of India, which is operated by CCA. And there are number of 20 plus certifying authorities are there. Some of them I just mentioned here. And there are subscribers, meaning we actually in the legal parlance we are referred as subscribers. So we approach them and then we get the certificate. This is how it works. So for a digital signature to have a legal validity in India, one must derive their trust from the root certificate, root CA certificate. So I would like to very briefly cover quantum threads and set the problem here. So as you know that I was talking about the RSA, the two pair of keys, public key and private key. So this public key and private key, this is actually they are generated by two large primes. When I say prime, it can be a 150 digit number kind of prime. So two prime actually, P and Q. So P and Q are multiplied and we get N. So this is how the algorithm actually works. But I will not get into the deep inside of the algorithm, but this is algorithm which is actually used in the digital signing process, RSA algorithm. So this public key, when I say public key, it actually consists of two components. One is a large composite number N, which is made of two factors, that is P and Q, two prime factors, P and Q, and there is an encryption component E. Now the private key relies on knowing the prime factors P and Q of N, as well as a decryption component D, which is derived from P and Q. So this is required, D is required. So public key is only the composite number N and E. But for doing a private key, when having a private key, I also know D, as well as I know what is constituting N, P and Q. That is the biggest secret. What are the factors of N? That is the thing. So in effect, if one can find out the factor of N, that is, if we can find out the P and Q which is constituting N, then one can get your private key. That is the idea. And there are algorithms which can do this, which is basically one of the algorithm, popular one is the general number field sieve algorithm, which can do this, but the problem is it takes a huge amount of time, exponential time, for getting this particular, doing this particular calculation. So for this actually, there is another algorithm which is created by Shah. So, which is basically, he breaks down the exponential time which is required. He has created an algorithm which can break it down. In a quantum system, it can bring it down to a polynomial time. So, that means the complexity is gone. But the problem is this algorithm requires a quantum computer to be done, meaning to broken. So, as CCS sir mentioned in the morning, Google thing about Willow, some kind of chip is required. So that is the thing. So SAR's algorithm uses the principles of quantum superposition and interference to efficiently factorize n. To factorizing that n, to find the prime factors of p and q, they need both of these things. And the problem is reformulated like this: finding an order r of a randomly chosen integer a modulo n, that is a to the power r, which is equivalent to 1 modulo n. So once r is formed, then you can apply this GCD, that is the greatest common divisor, a to the power r by 2 minus 1 by n, and GCD r by 2 plus 1 comma n. So these calculations can be done in a classical computer, but for finding a to the power r, which is equivalent to 1 mod n, that is a challenge. For that, what has to be required is you need a quantum system where quantum Fourier transform is required to find r in a polynomial time, because we are talking about very big numbers, so it's going to take huge time. So when you are talking to breaking down an exponential problem to a polynomial problem, you need this thing. So here what happens is we need a superposition where a quantum register can store all possible powers of a simultaneously and operate on it. And then we need a quantum interference where the quantum Fourier transform will process the periodicity of a to the power x mod n and identify the r efficiently. So after r is found on a quantum computer, the algorithm will use the classical, the system will move to the classical world and find out the greatest common divisor and derive the prime factors for p and q. So reducing the complexity from exponential time to polynomial time is the Shor's algorithm's strength. But the problem is Shor algorithms requires a quantum computer. And of course, a very simple integer like 15 or something, you can run around and you can break it up. But when you are talking about a very large prime number, 150-digit prime number kind of things, obviously this is not going to be, you cannot do it manually, you really need a quantum kind of system. So obviously, when the quantum kind of things come up, then really this is going to be a threat. Another algorithm I just thought of focusing is the Grover's algorithm, which reduces the search space drastically. Now let us say that there is a n-bit key, that means you need to find out what are the possible combinations, where could be the key. 2 to the power n bit is a search space. Then by using Grover's algorithm, you can reduce it to 2 to the power n by 2. So this is for the, if there is a AES 128 bit key, then you need to find out 2 to the power 128 chances are required to find out the exact thing. But using Grover's algorithm, it actually reduces by half, 2 to the power 64. And similarly, some other problems you can actually even break it further down by 3 also. So these are certain strengths of the Grover algorithm. So that these are the things which all require the power of quantum systems. So now, of course, tomorrow or sooner the quantum computers are going to be there. So for that, for surviving in that world, we need something called as a post-quantum cryptography. So that is the essence of this workshop. So even in a quantum thing, what happens is you use the post-quantum cryptography, but still it will not be breakable by a quantum computer. That is the objective of this algorithms. So this, sorry. So the objective of this post-quantum cryptography is, of course, they use techniques from lattice-based cryptography, code-based cryptography, hash-based cryptography, etc. So, and then lattice-based cryptography is what two algorithms have been standardized, which are associated with the lattices, crystal dilithium and crystal dilithium is used for digital signatures and it has been standardized by NSA, that is MLDSA algorithm. And crystal kyber actually is used by key encryption mechanism, that is CML-KEM. So these are the algorithms, and of course today's sessions and today's by external speakers will be covering all of this in more detail. So this is the, actually these algorithms have been coming out from NIST's challenge, and today NIST in the last month, in the month of October I guess, has standardized these two algorithms, MLDSA and MLKEM. And they have also given a timeline for all of the cryptography system to move from RSA, the traditional system, to post-quantum cryptography systems by 2030, by the year 2030. So that is the thing. So thanks for your patient listening. And if there is any queries, I can take it up. I will be there for the whole day, so we can take it up. Thank you.
sir, for enlightening us with the evolving and current trends in digital signature. I request Dr. Balaji to kindly present a small token of appreciation to our esteemed guest. Shri Arvind Kumar sir, please come to the dais for the token of appreciation. Professor Rahul Banerjee, Director sir.